All right, so I think we will go ahead and get started. We've got almost 200 attendees, so that's really nice. I'm glad to see so many people turn out this evening. Tonight we have two speakers who will be discussing the Nobel Prize in Physics that was awarded this year. We have Professor Predrag Cvitanović, School of Physics at Georgia Tech, and we have Dr. Erin, who is a senior lecturer at Emory and also the director of the Emory Planetarium. So without further ado, I will hand it over to Professor Cvitanović.
I don't know whether it's just me, but I dread the morning. I dread reading the news of what happened last night in this horrible year. So imagine my surprise when I look at the phone and I see Nobel Prize in Physics, Roger Penrose. Now, I would have never thought that Roger Penrose would get Nobel Prize because he deserves it. He's not an apparatchik. He's totally amazing. He's also a very sweet person. He's just not the kind of person who gets Nobel Prize. Look at my mouse. In the upper right corner above my bed, there's a book. It's called The Road to Reality. It's really by my bedside, and it should be by your bedside too, especially if you're taking any courses. It's a serious commitment. At 1,099 pages, 3 pounds. This is a book. This book is amazing, and I will explain why it's amazing. And I think the only fair thing I can do to Roger Penrose is to try to give you the world as seen through Roger Penrose's eyes. I cannot do his accent, but I want you to get a sense of what is it like to be a living, passionate human being like Roger Penrose. Occasionally, I will even slip in the first person. The story starts with a typical Penrose thing. Immediately, the moment he got his Nobel Prize, he was besieged by journalists, and they always ask the same question. What is your advice to young people? Penrose answers, advice to young people? Giving it is not a good idea, but okay. Do what you find exciting, do what you find beautiful. As a child, Roger was a boy flummoxed by problems of mathematics. Teachers reported to his parents, his problem-solving skills are too leisurely for school. And Penrose reports, I was moved down a class. And it went like this. He loved math. By age 21, he looked at his colleagues and he understood there were two kinds of people around. They all were committed to mathematics, but some of them thought visually, and some of them seemed to think linearly as a sequence of statements. And there were people like, some of them like music, some of them like art. He found it difficult to understand the equations that he was manipulating. So by age 21, he invented his own diagrammatical language. On the left-hand side, you can see the usual symbols and equations mathematicians use. And on the right-hand side, you can see his calculations. He draws them. Those are his typical calculations. Age 23, he went to a math congress in Amsterdam and saw an Escher exhibit. He came back, talked to his father, who is an impossible contrarian. The son and the father constructed the impossible tribar. The father was very interested in optical illusions, and they published this, and they went back to Escher with it, and Escher drew in return the impossible waterfall. At age 24, he reinvented an inverse of a matrix that has no inverse. If matrix has too many zeros in it, you cannot invert it. And it turns out our undergrads pay cool dollars for it to a criminal organization called CHEG. You can get the answer, you can get a Moore-Penrose inverse in real time while you are taking an exam. And today, it turns out it's every place. It's in neuroscience and big data. It was a little invention at age 24 with long repercussions. At 27, he decided, he knew nothing, he knew no physics. He says, I've decided I was going to start learning some physics in a serious way. I had to learn it myself because I'd never taken a proper physics course. Age 27. At age 27, two things happen. He finishes his pure maths PhD on something called tensors. Turns out to be very useful if you want to do general relativity. Second, he meets 29-year-old David Ritz Finkelstein. That changes both men's lives forever. And here is what Penrose says about it.
I think my older brother read me the Mr. Tompkins in Wonderland chapter and all that. It sounded fascinating. My friendship with Dennis Sharma, when I was in Cambridge, he befriended me very much. But it wasn't the case that I necessarily wanted to do it as a career. I think this came about more when I came back to Cambridge as a fellow, research fellow, and Dennis Sharma persuaded me to go to a lecture in London given by David Finkelstein. And he was describing how what had been commonly known as the Schwarzschild singularity, what we now call the horizon of a black hole, was not actually a singularity, and you could extend through it, and you had a singularity in the middle, but you didn't have this. So I came away, and we had discussions, and I got sort of fired up to do more general. I mean, he commented on this, that I told him about some of the things I was doing about combinatorial quantum mechanics, and he went in that direction, and then I went to general relativity, which had been his direction. But I think I was struck by the fact that even though this apparent singularity at the horizon was now not there, you pushed it somewhere else, you still had the singularity in the middle. And I wondered whether there wasn't some theorem about the persistence of singularities in some sense. This was a long time before I proved my own theorem many years later at the time. But I did wonder, what kind of methods could you possibly prove a thing like that? I had no idea at all, because I knew very little about the subject. But I had been studying spinors, because I'd been interested in quantum mechanics and tensor systems and what are spinors, and it intrigued me a lot. But this was the main thing I knew about, and so I tried to write general relativity in spinors. And lots of things came out so beautifully that I got hooked by the subject. I think that was the main thing. These things were quite fit together in a beautiful way, which I hadn't anticipated at all. And then that really hooked me.
That was the fateful meeting. What happened to Penrose is that he became a general relativist. And he says, and I agree with him, general relativity is not difficult to comprehend compared to quantum mechanics. Equations make complete sense. They're geometry. One can explain it, not entirely honestly, but rather quickly. The space is like a rubber surface, and if you put a planet or a star in the space, it bends it, and it falls in it as it would fall into a rubber membrane. And what had fascinated everybody working on general relativity up to that time was the question that if you put too much mass in a part of space, will it bend that rubber sheet so much that it'll fall into a hole? Now, what did Finkelstein talk about in his London seminar? He explained that you could take what is known as a Schwarzschild metric. It's one description of this bending of the space-time in neighborhood of a mass. And he explained that you could extend this description of space-time beyond what's today called a black hole horizon. And that is today a basic ingredient in current understanding of black holes. That even though you reach this horizon beyond, you cannot escape the black hole, inside of it you can describe the world and you can find that there's actually a singularity that we call a black hole. Now, this seminar was a revelation to Penrose. What happens after the seminar? There was a couple of hours of conversation between the two men, and it was totally amazing. Penrose explained to Finkelstein his ideas about quantum nature of space-time. or his spin networks, the two men exchanged their research subject forever after. I'll come back to this when I talk about spin networks. But Finkelstein picks up on the combinatorial aspects of quantum spin as a possible route to delving more deeply into the quantum nature of reality. And, says Penrose, he took such ideas to greater lengths than anyone else. Penrose, in turn, took general relativity, and that was it. They switched forever after. What is the problem with the early black hole solutions? Finkelstein's extension of the Schwarzschild metric, this description of what the neighborhood of black hole is, provided Penrose with an opening into general relativity. But everybody, in Penrose's opinion, and my opinion too, had assumed too much symmetry. They assumed that the neighborhood of a black hole was perfectly spherical in 3 space dimensions, and that the gravity pulled exactly toward the center. Now, imagine if you had lots of people with pistols and very high precision shooting exactly at the same point in space. Of course, there would be a huge concentration of lead at that one point. But if they made any errors whatsoever, the bullets wouldn't hit each other, they would scatter around, the mass would slosh in the bottom of this rubber hole. And how could not this assumption of perfect symmetry lead to a singularity? But what happens if you don't have perfectly initial condition, if you have masses that are coming into this hole from different directions at different speeds, etc.? People didn't believe it. They wondered, and so did Penrose at age 27. What if matter sloshes around? And indeed, here is a simulation done by Professor John Wise at Georgia Tech. It shows what happens if you have a gas that contains 10 to the 5 solar masses collapse into a black hole. In a simulation, you can see that these are different instants in time of density. And you can see that this is sloshing in a very complicated way. There is nothing symmetrical about this actual solution of gravitational equations. And until then, everybody thought, well, symmetrical singularity collapse, but any asymmetrical one could lead to matter coming in and sloshing out again, which would not be a black hole. Another thing I would like you to understand about these young people is how young they were. Here is Roger Penrose at age 31, leaning on this car. Standing in the crowd is David Finkelstein. And then you see everybody else. And what you see is, you basically see James Dean. You see 2 rebels and a bunch of nerds. Everybody else looks like you're supposed to look like if you are a theoretical physicist interested in general relativity, but not these 2 guys. These are 2 cool guys who listen to nobody and follow their own path. We'll now leave Finkelstein and follow Penrose. Age 31, he started thinking about general relativity. Remember, age 27, he knew no physics. He had to learn this stuff. Age 32, he already invents an important thing that everybody uses today. It's called Penrose Diagram. And basic idea of Penrose Diagram is that the only thing that really matters is stuff that moves at speed of light in special and general relativity. And that defines cones. Cones are very special because on them there is no time. They somehow interpolate about space and time. But they divide space-time into causal diagrams. Things inside can interact, things outside cannot communicate. In Penrose diagram, infinity in space or time gets mapped into the point that you can look at and you can understand qualitative features of structures that general relativity accommodates. So 6 years from when he starts being a physicist, he finally proves existence of black hole by bringing in something that he was very fond of, but it was not a natural thing to a general relativist. He brought in topology. Now, what is topology? Topology is rubber sheet geometry that deals with properties of objects when stretched. And, that's what strong gravity does, it stretches things. In, topology, for example, the little animal and the sphere are the same. The cup is the same as a donut. They have just one hole or one handle. The objects, like pretzels, that have 3 holes or 2 holes. And these are the things that topology captures. It captures the basic geometrical shape without focusing on how they're actually built and constructed. And what's new about topology, once you understand it, you actually don't need to solve equations. That's the brilliant idea that goes into his proof of existence of black holes. He's able to argue that trapped surface of any shape guarantees that once you fall into the black hole, you cannot slosh out. The technical argument is too subtle for tonight's story, and I will not pursue it. So what did he prove? He proved that you can put a surface around a black hole, what he called trapping surface, of any shape. And he proved with topological arguments, without solving any equations, that as you went through the surface, you could not come out again. Now, what that meant is that general relativity was known already to work. So it meant that black holes should be everywhere. Now, at that time, there were no black holes, and nobody knew whether they're very small or very big or anything. So, at age 33, he changes the subject of general relativity or black hole physics, and he publishes his Nobel Prize paper. On the right-hand side, you can see a typically beautiful Penrosian illustration of how the trapping works, and he's done. So we can stop this presentation. The man has gotten his Nobel Prize at age 33. We can go home. Not so fast. It took many years for astronomers to become less skeptical. Now, they're all on board. They already had a long experience with mathematicians and physicists who told them all kinds of things that they didn't believe and turned out not to be true. So, Roger Penrose remains Roger Penrose. At age 36, he invents twistors. One of the big questions that physicists always have to face is, why do we live in 3 space dimensions? Indeed, in much of the modern physics, people hypothesize many more than 3 space dimensions. Roger is convinced that there is a reason why we live in these 3 dimensions. To explain it, he invents what he calls twistors. Twistors say that our 4-dimensional space-time, that is to say 3 dimensions of space and 1 of time, is a mirror of a mathematical structure in 4-dimensional complex space which has imaginary numbers in it. And notice how he explains this with beautiful, beautiful pictures. He illustrates it in a beautiful way. These are all his transparencies, and this is how he communicates. At age 38, he and Hawking postulate cosmic censorship, and it basically says, yeah, black holes are out there, but they're all wrapped in some kind of body bags, and we can't see them. There is a principle which they call cosmic censorship conjecture, that black hole singularities are confined to an event horizon, and surrounding this hidden space-time region, we could actually, if we lived on the edge, we could actually harvest energy, because there's lots of stuff going on just on the edge of this event horizon with great amounts, and astronomically, unthinkably great amounts of energy is emanating from those regions. What's shown here is, you might have seen it, this is a beautiful photograph from 2019 of a black hole. Of course, we cannot see the black hole, but we can see a great deal of activity on the edge of the black hole where things are falling in and radiating. At 38, Penrose invents negative dimensions. So, what's a negative dimension? Line is 1-dimensional. The screen you're watching is 2-dimensional. You're walking through a 3-dimensional room. People who live special relativity, who understand that they actually live in 4 dimensions, they live in space-time. But mathematically, you could live in negative 2 dimensions. And it's actually very elegant and pretty to live in 2 dimensions. And look at his calculations. They're all done in terms of pictures. At age 40, he wants the answer to the following question. Students always ask me, is space continuous or discrete? And many physicists sooner or later comes to this point. It's quite possible that on our scale in meters, centimeters, angstroms, things look continuous. But if you had a very, very good microscope going to very small lengths, so there's something called Planck length, which is a typical gravitational length, maybe the space is discrete. How would you know it and how would you describe it? Penrose proposes to build our net space, the world that we live in, from little quantum spins, spin 1/2, the smallest possible spins. And again, his calculations are diagrammatic. You can see them right here. They're all visual. At 43, he does something that a general relativist should not be doing. He invents Penrose styling. Penrose styling is this amazing thing that a number of people have pondered, but Penrose brought it to the simplest possible essence. When you take 2 little tiles, 2 different shaped tiles, in such a way that they can fit together, and you start tiling the space like the floor of your bathroom. What's amazing about these tiles is that it looks regular, but if you look close to it, it's actually not periodic anyplace. Every region is tiled differently, no matter how big the floor of your bathroom is. By the way, these transparencies you can get from my website, and when they're colored links, you can click on them and you can see the things I cannot show you right now. Now, why is this big deal? This tiling disposes of centuries of received wisdom, going back all the way to Kepler. Kepler was searching for pentagonal snowflakes. And the consensus in physics and chemistry of 19th and 20th century was that you cannot build regular crystals from pentagons. That would not be possible. By the way, the drawings again are Penrose's drawings. And this went so far that when an experimentalist discovered crystals with pentagonal symmetries, fivefold symmetry, by experiment, he measured it. Nobody believed him. He was much abused. He was attacked by another chemist who had 2 Nobel Prizes, one of them for peace, but nevertheless. And eventually, the outcome of this discussion was that recently he was awarded Nobel Prize in chemistry for this thing. So this seemed like a strange little game, but it went in this contrarian spirit that you already saw at age 23, when his father, Escher, designed impossible tri-bar. Here they designed impossible materials and showed that they actually can be constructed. At any age, Roger Penrose has been a contrarian, always. He always derived a great pleasure in needling and irritating fellow physicists. One thing that works 100% if you want to irritate a physicist is to say very loudly, quantum mechanics is wrong. And he profoundly believes it, even though all the rest of us earn our bread by using quantum mechanics, and it hasn't done anything nasty to us for a century. It's miraculous what it's given us. The very fact that you're watching this screen is a consequence of advances due to quantum mechanics. For Roger, quantum mechanics is wrong because what's missing in quantum mechanics is description of gravity. He believes that gravitization of quantum mechanics is needed. That he shares with Finkelstein. The best thing that we have, it's wrong. One thing he cannot stomach is Schrödinger's cat. He claims we don't have a connection between quantum level of reality and classical level, the one that you see with your eyes, described by Newton, Maxwell, Einstein. At 58, he has to go to Odense where Hans Christian Andersen was born. So he draws this cute picture of a mermaid, which is both classical and quantum, has to be joined at the waist in a way that we don't understand how. And then at age 58, he goes New Age on us. He comes out with this book called The Emperor's New Mind. He has observed his friend Hawking make a pile of money on a book that nobody has ever read or understood. So he writes a book and he says, I don't know much about neuroscience, but he argues that quantum mechanics is a fundamental component of consciousness. He drives us all totally crazy. Truth, beauty, morality, triality, duality, three worlds. Consciousness, it's so difficult, it must be quantum mechanical. We're all furious, not just evolutionary biologists. He arouses the fury of everybody for debunking ideas about human consciousness. He goes on, in 1963 he writes Shadows of the Mind. He looks for missing signs of consciousness. He joins forces with anesthesiologist Stuart Hamernoff. And, there are more and more these beautiful pictures of axons, neurons, etc. He uses all kind of physics worlds in neuroscience. And then on the side, at age 66, he sues Kleenex quilted loo paper for using his copyrighted patent. And he wins. He wins the court case. And we're not allowed to know how much he got out of this by the terms of the agreements. The famous non-disclosure agreement. In 68, writes another book on science and the mind. In 69, in a collaborative effort with Vanessa Penrose, very wonderful woman, they together produce a son, Maxwell Penrose. And finally, at 73, having been harassed by his colleagues now for decades, colleagues, he says, like my equations, but not the contentious stuff about the mind, and urged me to write a straightforward book on physics. I thought it would be a simple scissor job, but it didn't turn out that way. Decades of work went into this book called A Complete Guide to the Laws of the Universe, the one that's above my bed always. And it's an amazing book, all in pictures, as you can see a typical page inside the book. They want him to write a book about something that he knows something about. 8 years later, he produces the Complete Guide to the Laws of the Universe. I'll show you some illustrations, and this is Penrose. They're beautiful, and they're extremely helpful in explaining the material. It's very mathematical material, but this book makes it approachable not to the every person it was supposed to reach. To my students and myself, it's invaluable research to go back over and over again to get some intuitive picture of the mathematics that we do in our research. At 75, he comes with an outrageous solution to a profound cosmological puzzle. And what's the puzzle? Most of us have accepted that our world was created in a Big Bang, the universe that we live in. Now the question is, what was there before the Big Bang? He goes to Copenhagen to a birthday party to give a talk as a birthday present. And it's a cosmology of eternal rebirth. And again, you can see the typical Penrose transparency, visually beautiful. We didn't understand anything. We were barbarians. We did not get it. Penrose says that there is no one universe born in a Big Bang. Evolution of universe goes in cycles of time. Again, illustrated beautifully. One Big Bang, our universe is on the left, but it's supposed to match up and then topologically be this cylinder on the right of eternal falling in and expanding again. And it's an active area of research. Roger and collaborators see evidence of earlier universe existing before the Big Bang of our present universe. It's repetition of what he did at age 33. The Big Bang is only an apparent singularity, similar to the apparent singularity at the event horizon of a black hole. Conceptually, it's a very similar thing, but now we're talking about entire universe. That happened at age 75. And the reason why we did not understand in Copenhagen what was going on is because all Roger would talk about was about Sri Lankan cricket team in England in 2006. So it was all about cricket while he was in Copenhagen. So that's the only thing he wanted to talk about, cricket in Sri Lanka and England. In 1984, he joins an effort, popular science effort, to teach children how to draw to be able to do math and science. At age 85, he writes a screed called fashion, faith, and fantasy in the new physics of the universe. And it's a screed against his colleagues who follow fashions and think religiously and in terms of fantasy. So he's a contrarian, and we love him. He might be a Nobel Prize winner, his most friends and admirers ever, because he's just such a lovable, passionate, creative, thinking human being. Here he is with Mitchell Feigenbaum and myself, and we are so grateful to have him. And now I would like to hand off this presentation to Erin, who will tell us about the real stuff.
All right, thank you, Predrag. It's going to be incredible. Just wait. Okay, so I'm going to discuss the second half of the Nobel Prize, which was awarded jointly to Reinhard Genzel and Andrea Ghez for the, and this is the quote from the Nobel citation here, the discovery of a supermassive compact object at the center of our galaxy. The word black hole does not appear here, right? So it seems that even the Nobel Prize Committee is not yet on board with the idea of black holes. So as we heard earlier, it is true that it took the astronomical community a while to come around to the idea that black holes were real, but in another sense, the idea of a black hole predates all of this work by centuries. So the first idea of a black hole dates to the late 18th century, and here is Laplace, who is calculating what would the mass and radius of a hypothetical star have to be such that the gravitation at its surface was strong enough that it would equal or exceed that the escape velocity from the surface would equal or exceed the speed of light. And he comes up with an answer, and he's quite right about the mass and the radius, or he's extremely close, although there is no such thing as a star 250 times the size of the sun with density equal to the Earth. Such a thing would collapse into a black hole. So not only was the idea of a black hole known at this time, but also the way to discover them. So Laplace was predated by a few years by an Englishman who made the same calculation. And he was thinking in terms of binary stars. And so, whereas Laplace back here says at the last sentence, they're the largest bodies in the universe that may thus be invisible by reason of their magnitude, he's thinking about if there's some luminous body, such as a star that revolves around a black hole, we could infer their existence. And he says, but the consequences of such a supposition are very obvious, and it's somewhat beside my present purpose, so I shall not prosecute them any further. So perhaps we may have had the first discovery of a black hole in 1784, but as we shall see, there are a bit of technological difficulties with carrying out this project. But this is the way that the supermassive compact object, I'll call it a black hole, in the center of our Milky Way was found. It was found by looking at luminous bodies, stars, orbiting around it. Okay, so I'm going to give you a little bit of introduction about a black hole. And just like Penrose here, I'm illustrating the equations so we don't have to think too much about them. So these are the equations of general relativity. And I'm not going to explain the details, but what we have is mass on the right-hand side. So those terms there tell us about all of the stuff, the matter, the energy, the bowling ball on the rubber sheet. And what happens when you place a bowling ball on a rubber sheet? The rubber sheet is curved and deformed, and that comes in on the other side of the equation. We have some terms that describe the geometry of space, how space is curved. There's another term that includes the dark energy that accounts for the increasingly expanding universe, which is a subject of a different Nobel Prize altogether. And then there's some calculus in there. So these are the equations that Einstein developed to describe how mass affects space. And here we have the first solution of this for a Schwarzschild black hole. So this would be a Laplacian black hole, just a simple mass, which has an event horizon So the radius of a black hole, we say, is the event horizon, and that is the point at which the escape velocity is equal to the speed of light, and it's related to the mass of the object. Now, you heard Penrose talk about the singularity at the horizon that he was trying to get rid of. So if you look at these various terms here, what's that equation doing up there? It's telling us about how space and time interact. So that first term, you see a dt, t is for time. And so if we imagine what happens at the event horizon at 2gm over c squared, the thing in the parentheses in front of that goes to 0. So does time stop at the event horizon? Your clock must turn off as you cross the event horizon. That seems odd. And if you look at the second term, dr, that's like the radius, and we would get a 1 over 0, some infinite term there, which physicists don't like whatsoever. So this is the singularity at the horizon, which Penrose shows is not a physical singularity. Here is another type of black hole. So Schwarzschild, 1916. Add angular momentum to a black hole, it's going to take you a few decades. So in 1963, we have the expression for a rotating black hole, and that's a lot. We're not going to discuss that equation there. And you look in the lower left, we have a much more complicated structure with event horizons and singularities. And this is what Penrose was contemplating when he came up with the idea of a collapsing star forming what is known as a trapped surface, which would be the generation of the event horizon. And you see there Penrose's drawing on the right, which I think we have to agree is a little bit, has a bit more character than the one from the Nobel Prize organization, which is on the left. Okay, so to show you a couple of Penrose diagrams before we talk about discovering the real black hole, because I think it's kind of interesting and it addresses some of our science fictional aspects of black holes. So this is a way of representing those equations that I just showed you. This is for a Schwarzschild black hole in the form of a diagram. And as we look at this diagram, you see on the right there, there's a blue dot. It's a little particle that is moving forward in time. So time goes up in this diagram. And you see it crosses the horizon with no problem. It doesn't have to turn off its clock. And once it crosses the event horizon, it lands on the singularity. And we can have light going off in different directions as well. And what Penrose showed with these diagrams is that you can extend them. So on the left, you see a Penrose diagram for a Schwarzschild black hole that contains the other half of the math, basically. This is the idea of a parallel universe being attached to a black hole. Over on the right, when we have a rotating black hole, we get very interesting paths into the black hole and then out into another universe. So we see in these mathematical descriptions the possibilities that extend beyond simply locating a black hole in our galactic neighborhood. Is the black hole in our galactic center a portal to another universe? But it's fun to think about. Okay, let me go back just a few things here. So here's Penrose and his Nobel Prize winning paper. And notice how he leads off up there in the upper left. He's thinking about the discovery of quasi-stellar radio sources, which has given a kind of impetus to thinking about gravitational collapse. So astronomers are coming around to the idea of a black hole because they've discovered some quasi-stellar radio sources, some oddball objects that they think might be connected to a black hole. And those are the quasars. So we'll go back past here. Okay, so the first quasar was discovered in 1963 by Martin Schmidt. You can see him honored on the cover of Time magazine back when astronomers were honored on the cover of national news magazines. And what he observed was a star-like object. So in the lower left there, you see a Hubble image, looks kind of like a bright star, but it had a very large redshift. And what that means is that it was very far away. So we know the universe is expanding, causing things to have a redshift. And if it was as far away as the redshift would indicate, it must be more luminous. It must be about 1,000 times as bright as the galaxy. And if you look in the right-hand image there in the center bottom, you can see a little bit of fuzz around the image. That's the galaxy. So there's something in the center of that galaxy that is producing enough energy to outshine all of the other stars in the galaxy. So this is what astronomers were confronted with observationally, and why they just so happen to have some theories regarding black holes that would explain this. So in 1969, Donald Lynden-Bell proposes the idea that quasars are run by black holes. That is, the falling of material onto a black hole that produces this incredible amount of energy. And it's interesting to me to see this old-time language. So instead of referring to an event horizon, he's thinking about the Schwarzschild throat. And so he expects to find them in the centers of nuclei of galaxies. And, excuse me, then in that second paragraph, he expects that these collapsed bodies, these black holes, would have a broad spectrum of masses, 10 to the 10 to 10 to the 11 solar masses. That's about the upper limit of supermassive black holes, while normal galaxies like ours may have only 10 to the 7 or 10 to the 8 solar masses down their throats. So it overestimates it a little bit. But this is the first idea, that if we have matter that is falling onto the black hole, it, in the process of falling, will heat up to incredible temperatures, and it will be compacted into a very small region before it crosses the event horizon and we no longer see it. So what a quasar is an actively feeding black hole, which suggests that when the black hole is done eating, there should be a collapsed old quasar, there should be a supermassive black hole as a relic of this earlier period of active accretion. And that indeed is what we believe the supermassive black hole in the center of our galaxy to be. There's no quasar in our galaxy. It would not be good if there were, but there is a supermassive black hole. Okay, so there's the galaxy. And if we have this idea that there might be a supermassive black hole in the center of the galaxy, well, we'll just go look for it. There's a bit of a problem with that. We are quite a ways away from the center of the galaxy. So we're about 26,000 light years from the galactic center where the supermassive black hole is. You can see the map down there in the lower left if you'd like to take a visit. And even more importantly, the galactic center, which you see there in the image of the Milky Way, is highly obscured in visible light. All of those dark patches that you see are regions of cold, dense interstellar clouds that are absorbing light from the stars behind it. So in order to see what's going on in the vicinity of the black hole, we need a way to see through all of that stuff. And so the way this is done is to look in longer wavelengths of light. So if I show you this image here in infrared light, a lot of those dark patches go away and we see the stars behind. And this is due to the fact that longer wavelengths can more easily pass through the gas and dust. And if we look in radio wavelengths down at the very central region, a central few hundred light years in the galactic center, we do indeed see that there's quite a lot going on there. Those little bubbles that you see are supernova remnants. So they are the little popped bubbles of exploding stars. And you see various gas moving around. And in the very central region where you see SGRA, that's Sagittarius A, there is a source of radio emitting material that is interacting gravitationally in the vicinity of the black hole. So the location of the galactic center is in the constellation of Sagittarius. So if you're ever out looking at Sagittarius, you can imagine you're looking towards the supermassive black hole. Okay, so how are we going to find the black hole? So if there are stars orbiting a black hole in the galactic center, which there are, they will move similarly to planets orbiting the sun. We have a smaller star orbiting a more massive black hole. And in the lower left there, you see the speed of planets versus their distance from the sun. And the closer in they are, the faster they move. So we would want to measure the speeds of the stars in the vicinity of the black hole. And we also expect that the orbits will be elliptical, with the black hole being the center of mass at one focus. And on the lower right there, you see the orbits of some of these stars that are in fact orbiting the black hole. But this poses a technology challenge, because these stellar orbits are around a black hole that is 25,000 light years away. And if you look at the scale on that figure in the lower right, that's a fraction of an arc second. So there's 360 degrees in a circle, 60 minutes in a degree, and 60 seconds in a minute. So these are very, very tiny positional changes that you're going to have to measure very accurately in order to identify the black hole. And this is what our two teams, who won the Nobel Prize did. So beginning in the 1990s, Reinhard Genzel with his researchers in Germany and Andrea Ghez begin developing the technology to do this. And initially, a method called Speckle Imaging was used. So if you look at that little animation there, this is a star twinkling. Why does a star twinkle? Because the light is passing through the atmosphere. There's all sorts of air currents moving around that distort the image of the light. And so if you were just to take an image of a star, it would be kind of spread out, and you wouldn't necessarily see those small changes in position. So what they did was they developed this method of taking multiple short exposures, and then you combine them together in order to reduce these twinkling effects. And you see on the right there a figure from one of Andrea Gez's initial papers showing the resolution of stars in the central square arc second of the Milky Way. And on the bottom there, you see the two observatories where these two teams were carrying out their work. So it's good to have two competing teams. They really spurred each other on in order to make sure that the method is working, that the data are good, that the observations are indeed showing what we see. Here are some early results. So this is from 1997 from Genzel's group. And what's going on there in the lower left, you see those arrows. They're measuring the velocities of the stars, how they're moving in the sky. And in the upper right, you see something that looks very similar to that figure about the planets. The closer in towards Sagittarius A star, the location presumed of the black hole, the faster they go. So, yay. All right, but there was a limit to that. So you have to take lots of short exposure images, which limits how faint an object you can see. You need to have plenty of time on your telescope. And so in the early 2000s, another method came into use, which is called adaptive optics. And the way this works is you have a deformable mirror. So the mirror in your telescope can shift to counteract the distortion of the atmosphere and remove the twinkling of the star. So there is a laser guide star that simulates a star. The telescope can then adjust itself, kind of a simplified way of putting it, but we're running out of time. So in so doing, it can, in the same way, remove those atmospheric effects and make a precise location of the star. And also that light from the star can be fed into other types of instruments. So for example, you can measure the Doppler shift of those stars and see not just how they're moving sideways on the sky, but moving towards and away as well. And here is an illustration from Andrea Gez's group showing the improvement in resolution that you get with adaptive optics. And notice these images are taken at wavelengths of 2.2 microns, so in the infrared. And here is the famous movie. So, should move, there we go. And notice in the upper right, these are the dates. So beginning from the mid-90s on into 2000s, and those little blobs are the stars, tracing out beautiful elliptical orbits. We actually see it come around again. And the location of that little cartoon star, 2018, that close-in star made its close approach. That star called SO2 or S2. So let us watch one pericenter passage. This is amazing. So what do we see? We see luminous bodies revolving around a center of mass, which is not a luminous body. This is the supermassive compact object in the galactic center. Okay, so from those elliptical orbits, you can calculate what the mass is. This is freshman physics, and it's a little over 4 million times the mass of the sun. There is no 4 million solar mass star. Doesn't exist. Anything of that mass is going to collapse to a black hole. And so that gives its Schwarzschild radius or event horizon size to be about 13 million kilometers, which is about 18 times the size of our sun. So imagine 4 million times the mass of the sun within a volume nearly 20 times, within a distance about 20 times from the center of our sun. So incredibly compact. And note the citation, the discovery of a supermassive compact object. There is no other known object at this time than a black hole that can account for such a massive compact object. It's a black hole. That said, that's my personal opinion. That star that you saw, SO2 or S2, its closest approach to the black hole is 1400 Schwarzschild radii. So if we're thinking of exploring what happens when something crosses the event horizon, what's the nature of space-time at the Schwarzschild radius itself, where the strength of the gravitational field is profoundly strong, these stars are nowhere near, right? We're using freshman physics to calculate, that's a bit overstating it. But in fact, these stars do not get very, very close. And so there is still some open question as to perhaps there's another description of a compact object from some other physical theory which could account for it as well. Hence the hedging language right there. Okay, so if there's no 4 million solar mass star, where did a 4 million solar mass black hole come from? And this is an active field in theoretical astrophysics. And we imagine as the galaxy forms, there's some gas in some dark matter. Never mind about dark matter at the moment. And there's various paths. You might have a few stars per galaxy that collapse to a seed black hole. We might have an initial black hole form from gravitational collapse. We might get a star cluster forming. This is the lower sequence. But in any rate, we will always end up with a seed black hole, which over time, during the quasar phase, as mass falls across that event horizon, it doesn't come back out. So it increases the mass of the black hole. It grows the black hole to this size. Okay, here are some beautiful images of the pericenter, the point of closest approach of S2 in 2018. And when these teams analyzed the data, they were able to confirm several predictions of general relativity. With the star coming back again, they could measure the precession of the orbit, the fact the orbit changes orientation in space. And you may have heard that one of the first successes of Einstein's general relativity was to explain the precession of Mercury's orbit around the sun. So we see this here as well. Likewise, when light moves away from a massive object, it loses energy. It's like if you throw a ball up, it loses energy. And that causes the light to be gravitationally redshifted, and this was observed as well. But as before, the closest star is not quite in the general vicinity of the event horizon. Okay, so what can be done there? They will continue to monitor these stars, obviously, because the more precise the measurements, the more precise they can correlate the measurements with these various predictions of general relativity. Also, there's a lot of gas there. So we do see sporadic flares from gas and other, streaming. We see sporadic flares from gas falling into the black hole that come from much closer to the event horizon. And then also, as we heard a couple years ago, the Event Horizon Telescope was able to image an event horizon shadow in another galaxy, in the galaxy M87. They also took long observations of Sagittarius A star, of this black hole, and they're continuing to analyze that data. So perhaps we will have unforeseen surprises and new physics as we probe ever closer to the monster in the heart of our galaxy. Okay, so that's all I have to say. I'll close this out and send it back to our moderator.
Sumda Kanokler asked, how powerful do our telescopes need to be in order to measure the position of SO2?
Okay, I'll take that because Sumit is one of my students over at Emory. So hello, it's good to see you. And this question about how powerful do the telescopes need to be asks, what do we mean by a powerful telescope? So what makes a powerful telescope is that it can see something faint, and it will be able to see something faint if it collects more photons. So the power of a telescope is related to the size of the mirror, the bucket that collects the light. And in the case of these observations, they're using 8-meter class telescopes. So the diameter of the Keck telescopes, for example, that the Ghez group is using, is about 8 meters. And there are very few of these telescopes in the world, and time on it is incredibly competitively fought for. But
is that I was going to say, is that the largest telescope in the world right now?
At the moment. So there are even larger, there are 30-meter class telescopes in development. One of them, if you are aware of the controversy of building more telescopes on top of Mauna Kea, one of those is the proposed telescope, and then there's another one in the southern hemisphere. So not yet, that's kind of the next stage in telescope development.
Ramon Franco asked, what is the S radius in this case?
Schwarzschild radius? The question means what's the Schwarzschild radius of the black hole at Sagittarius A star?
Yeah, the monster at the heart of our galaxy.
Heart of the galaxy, about 13 million kilometers. So there's a really nice trick for calculating the Schwarzschild radius of anything that you're interested in, is you take the mass in terms of the sun, so the sun would be 1 solar mass, and you multiply it by 3 kilometers. So if the sun were to become a black hole, we would have to compress it within a radius of 3 kilometers. So take any mass you like, take your own mass and convert it to solar masses, multiply by 3 kilometers, and that will give you the Schwarzschild radius of anything you're interested in. For a Sag A star, it is about 13 million kilometers, which is well within the orbit of Mercury if we're kind of comparing it to the solar system. A little bit larger than the sun, well within Mercury's orbit.
JF asked, what is a white hole?
Predrag, you're the theorist.
There is no white hole.
Yeah, it comes out of I showed it. It shows up in the Penrose diagrams. If a black hole is something that once you cross the event horizon you can't get out, a white hole is the reverse. It's something that once it comes out of the white hole it can't go back in. So incidentally, it was originally kind of in the more speculative corners of astrophysics, like at the bars and conferences, the idea that quasars, maybe they're black holes. They're producing so much energy. Maybe there's energy coming out from a parallel universe at a white hole. So that kind of went the way of science fiction. That's mathematically what a white hole is it's basically the inverse of a black hole, but there's no astronomer of any sense who thinks that such things could possibly exist. There's no formation mechanism. There's no theory for why they would actually be there.
Well, thank you again. It's been a great talk and a fun evening. And thank you to everyone for attending.
Yeah.
Thank you very much.